Hey everyone. Today we are joined by Wojciech. Wojciech is a Scala tooling developer with VirtusLab. Today he's taken us all on a deep dive into Scala Native internals. So Wojciech, jump right in.
Okay, thank you. Hey everyone, my name is Wojciech Mazur. I'm a Scala engineer working at VirtusLab, and I'm part of the division specializing in Scala tooling for our customers. And also, we actually contribute for Scala Free. For example, we are responsible for the new Scala Free doc, or there are some people who are working on the matters. In July 2020, I was given an opportunity to become a community member of a Scala Center team and to work on Scala Native. And that's what I do basically now. So today I would like to tell you something about this project, especially how it works under the hood and how we did to manage to get rid of the JVM and to provide interop with native libraries. We basically talk through the whole compilation pipeline of Scala Native, and in the end, I hope to share with you some our goals and a roadmap from Scala Native in 2021. So without any further ado, welcome for deep dives into the Scala Native internals. So for the ones of you who don't really know what Scala Native is, it's a project that was originated at EPFL by the National Berlin, and it targets to remove the JVM backend from the execution and to compile code directly to the native machine language. And you may ask why to do this. So basically, when we run a code, we need to perform class loading, which introduce a lot of overhead when starting applications, and also basically code interpreted by the JVM is not as fast as it could be when it would be compiled to machine language. It's because when you run actually a Java application, you're actually running a Java interpreter, which then reads all the instructions and executes them. In some way, it's mitigated by, for example, just-in-time compiler, and that can transform this interpreted code into machine code and include it. However, it also comes with some drawbacks. For example, you need to perform a warm-up of the whole JVM, as well as you need to collect some profile from the program to be able to correctly optimize it by the hotspot optimizer. So the main idea is to remove all these dependencies, which introduce overhead for both memory usage as well as startup, and compile codes directly to machine language, which is kind of not so trivial task. And so, as I said earlier, it was created. This project was created by the EPFL, and it also includes a ahead-of-time compiler that is responsible for optimizing of these instructions that are created from Scala. It also comes with some runtime provided, and also, which also is containing some parts of Java standard library, on which in some parts Scala is dependent on. Since 2020, this project is maintained by Scala Center, and basically for quite a long time, it was about a bit behind the ecosystem, and there were no major releases. And the past year, we've managed to compile it and cross-build for Scala 2.12 and 2.13, as well as provide some new features to bring new freshness to the ecosystem. Other things that include that are included in Scala Native are a few implementations of garbage collectors that are used, and also, as I mentioned earlier, it comes with this really performant optimizer called TensorFlow. It was basically created mainly by Dennis. It was also part of his master thesis. And if you look in the web, you can find easily his doctoral thesis when he describes it quite in much detail. However, today we don't really have the time to do this. One other thing for people new with Scala Native, if you want to know something more about it, you can probably find on the web recording from last previous of Scala Love conference, in which Richard Whaling gave a really good introduction to the work system, where it works the best, and what can be in its some best use cases. So, how it's actually made? How to make code that is normally running on the JVM be executed as a normal program? Well, basically everything starts, the core of the world Scala Native is basically its native intermediate representation. It's an additional format that is introduced to make some mix from tasty type system as well as LLVM IR, to which Scala Native is in the very end compiled to. So it's mainly based on LLVM IR. All this and contains a subset of its low-level operations like stack allocation, loading, storing, adding values, etc. However, it's also enriched by a lot of high-level operands. So we have a definitions of classes, traits. We have some rich references with types. We also have some high-level operations that allows us to make it more efficient and easier to optimize. So, for example, if you, for example, take a look, for example, a class allocation. Instead of making a few operations that are needed, so for example, calling GC to allocate some memory and then call constructor on it, we simply in NIR, when generating it, we simply introduce a simple box operation, which can later be optimized in the next steps. Also, it contains some additional informations that can be used later. So for example, some linking hints, so we can collect informations about libraries to which we should also link, and they can be defined in the code itself, as well as some additional informations like when to inline some methods, when, for example, some methods should never be inlined, which can be sometimes can be quite helpful, as well to extern which definitions are basically defined in some external context. In the very base, NIR is the same as LLVM IR, a single static assignment based, which means that every operation, every result has its own unique identifier without the given block scope. And you cannot just simply add two identifiers to them. So, for example, if you want to mutate some state, you need, for example, to stack allocate some value and then update the pointer, which is created underneath. In NIR itself, and as well as LLVM IR, there is no some explicit types, for example, for pointers. All of them are created basically in the compile time in LLVM. Also, under contrast to LLVM is this that NIR is really strongly typed, and because there we can in LLVM we can basically just, for example, store information that something is a pointer. However, we don't really know what's hiding underneath. And in NIR, for example, we have rich information about, for example, some given class that is stored in some pointer and which can be accessed. This allows us for many nice optimizations in the optimizer. as well as we can add some additional attributes to it. So, for example, we can, add information: is this some given reference type an exact class? So we already know that it has only one single implementation, or is it, for example, or do we need, for example, to create some virtual method dispatches for it? Or we can, for example, look around and tell exactly if given type is nullable or not. So we can, so later in the optimizer, we can basically remove some checks and make the code run quite faster. Another thing worth to mention is this, that all the definitions in NIR are basically stored in one single top-level scope. This means that we also need to provide some naming schema to make them globally unique. We basically have such schema to basic definitions. We provide basically just two types of top-level members. So we have top-level members, which are basically some definitions of classes, as an example, and member definitions, which are, for example, methods and traits contained within these classes. For those, for example, we concatenate the name of top-level definition with some additional information about the signature of member. So we, for example, add some information about: is it a field, is it a method, if it's a method, which types is it taking as a parameters, or what its return type. Basically, it's quite complex stuff. But you can easily get into it. And for example, if you take a look, for example, some textual format of NIR that can be created when debugging and when some specific setting is enabled, and then we can look around and see what was exactly generated for given operations. Here we have some simple class, and we can see that basically it is some object, both by the module identifier, but also by the symbol right here, as well that it extends some foo class and implements bar trait. We already have this information in NIR. Also for some methods which are defined in it, and as well as their attributes. In this example, we know that this method, defined main, should never be inlined. We also have some additional informations about the function, because the main method is a function, and we already know which parameters types is it taking. In this case, it's this type for the test module, as well as array of strings, and it returns nothing. So when we know basically on which we operate in longer term in the world Scala Native, let's take a look at the overall pipeline of the execution and the compilation of Scala Native. Let me just take a sip. Okay, so basically there are two stages. The first one is a compiler plugin. It attaches to a Scala C compiler in one of the latest phases. It's basically somewhere before the number 5 phase, somewhere. So basically almost in the same place where the JVM bytecode is created. And so at this place, when we are actually attaching to Scala C compiler, all the heavy stuff was already done. So the syntax was already parsed. We already have all the informations about type system, about types, and there were already done some cleanups, the sugaring of the code. So we basically work on some already prepared classes. As well, the structure was already flattened, because earlier in the flatten phase, which is a few phases earlier, for example, some nested classes are moved to the top level, so we can easily operate on them. So basically, what compiler plugin does, its main job is to transform Scala abstract syntax trees to an IR format. In most cases, it's quite straightforward, but we'll talk about it later. Let's discuss how the Sbt plugin works. So in the Sbt plugin part, we have a few phases. The first one is linker, which joins all the files coming from both external dependencies as well as the output of the compiler. Then we have optimizer, which optimizes all the code. We have some special phase in which we are injecting code to our scope, as well as we're lowering all these high-level constructs to sequences of low-level operations. And at the very end, we are connecting with, we're transforming our code to LLVM IR and using Cloud compiler to compile all these sources, both this which are coming from the user, because user can provide his own native sources, as well as sources created from Scala Native. So, as I said earlier, the main job of compiler plugin is to traverse basically all the abstract syntax trees in each compilation unit while compiling. So every time he finds some class or class definition or method of value definitions, it tries to create its counterpart from it in an IR. So basically, for example, it creates a class in it. At this stage, we are basically also collecting a lot of informations. For example, types. So we get information about the parent type of given classes, traits that are implemented by it, but also a lot of attributes that are basically, in most cases, coming from annotations in the code. So basically, for example, no inline annotations or definitions of external methods or objects. On this stage, we are collecting all the positions from AST. We are not really using them, but in the future we are going to provide full debugging support, so we can easily track your code when executing with some special tools like LLDB, or maybe in the future even in the IDE, like metals, for example. At the very end of the compiler plugin pipeline, we are simply creating a binary. We are serializing all these NIR definitions that we've collected in the runtime, when traversing these trees, to NIR files, which are quite similar to class files that are emitted in the JVM phase when emitting bytecode. So maybe also let's take a look what are, in most cases, transforming Scala trees to an IR is quite straightforward. So for example, we have some apply method, so calling something, and we can easily translate it to an IR with some additional checks for the input methods and checking, for example, for boxing types. However, there are some cases in which we need to provide some additional logic. For example, when generating, for example, external functions. I mean, in case when we want to, for example, use a function defined in Scala and by pointer pass it to native library to use, for example, in case of some event that is as registered callback, it's not really so easy. So basically, for example, we cannot pass it like just straightforward because based on the ISTs, we would just provide an object to the function, Scala function object, instead of actual function that should be executed. And to the help comes all the set of some intrinsic internal functions that we use to define some low-level operations. In most cases, basically in all cases, it's not possible to define some behaviors in Scala syntax. However, it's quite easy in the compiler phase when we already can create an NIR basically by hand. So in mentioned situation, instead of passing object to the class, we can transform it to pass only the pointer to actual function, which is pointing to the method in this object of C function pointer. And additionally, we can add some additional checks to it. So for example, if most cases, we assume that types in Scala Native are boxed. However, in the native libraries, there are always using just some primitive types. So we can inject some handling that needs to be done. So when native library calls function defined in Scala Native, it first needs to box all the parameters, execute the real code, then come back to the execution point of execution and unbox the result of this function. And then you can work without any further problems. By using such mechanism, we can basically implement all these things that are not possible in any other way. So, for example, stack allocations, some row pointer operations like loading, storing, and manipulations. So it's quite useful. However, when we have already our code already generated, yes, because compiler plugin is just a part of the bigger ecosystem. It's just a front end for Scala Native. What happens next when we have already our code compiled? We basically try to link all the stuff together. So we join both the NI files coming from the class path of external dependencies, because each project that is compiled with Scala Native contains not only class files, which are used for compilation, but also they contain NIR files used in the link time. That's basically why, for example, if you try to use some library that wasn't compiled to Scala Native, you basically get some linking problems. So at this stage, we're just trying to, from each entry point that is defined in our configuration, we try to try to traverse a code and all these operations that are done. And basically, like a regular class loader, we try to fetch some, to reach each of the definitions that are needed on the runtime. In JVM, it happens in the runtime because there's no basically other way. However, in Scala Native, it always needs to be done ahead of time because, well, there is no native program where we just need to load stuff like this. At this phase, we basically all the stuff that is not reachable at linking. For example, if we haven't reached some methods or some classes, they are basically discarded and not taken any further. So thanks to this, we can basically just remove the size of the output binary, as well as speed up the next phases in which we don't need to optimize methods that are never used. Also this phase, we are collecting a lot of metadata from classes and their members, so that can be used in the next phases. Also, we check for some allocations on classes, because still, if some class is not allocated, we can easily discard it, because it's never actually used. So basically, when we have our code linked all together, we can move on to optimizer. In fact, it's an optional step. However, I guess that it's run almost always. Yeah, so I don't really have time to go to some really big, deep details of it. However, as I said, you can check out the master thesis, doctoral thesis of Denis Shabalin, where he describes interflow optimizer very well. I'm just going to talk about some techniques that are used, the most frequent, and are combined in it. So the first one is basically inferencing type informations by the control flow. So it means that we can check at given point if the instructions does given, for example, if given type, for example, is nullable, if it's an exact type. So based on this, we can later provide any other optimizations. For example, if, for example, class is never known to some given operand, some local value is never going to contain a null, we can easily discard all the null checks which are checking, for example, it, because this condition would never fail, basically. Also, we can then, for example, apply other optimizations like inlining, which is quite straightforward and it basically doesn't need any further explanation. Also, there is a polymorphic inlining, which is quite more interesting because we can basically inline code from many different implementations of given class. And then in the runtime, we can basically just create some if checks based on the actual runtime informations and execute them without creating any drawbacks and overhead due to calling it. Another thing is partial evaluation. So, for example, if some things are known at compile time to have some value, or there are some known rules that we know how to behave, we can easily remove some checks and make it a bit faster. Also, one of the most important in terms, for example, of boxing and boxing types is partial escape analysis. So in this type, we can, for example, check if given value ever escapes its actual context. For example, if you would need to pass it to, some another function, we would need to box it. However, if it never escapes it, we can easily keep it as a primitive type, and again can speed everything up. Also, thanks to this, we can delay some allocations of the classes, as well as allocate some things only once. So it's really helpful method. Also, the last one, method duplication, also kind of straightforward. So we can duplicate some generic classes to make code work a bit faster. Another phase, after the code is optimized, we are going to our code generation phase. So in this phase, we are again running static reachability checks, because some methods or classes may not be no longer reachable after the optimizer run. However, this part is a bit faster because it all happens from the memory loaded definitions. However, based on that, we can finally create some concrete memory layouts of the types defined, as well as there are virtual tables used for dynamic methods dispatches. Also, this stage we can inject some code to our program. For example, at this stage we are injecting the real main loop, which is calling the one defined by the user, And there we can, for example, prepare our execution context, which is basically still kind of limited, or to initialize all the class initializers, or prepare some module accessors, as well as prepare on all these runtime informations and metadata needs later. Next phase, which is lowering. So as I said earlier, we are translating all these high-level operations, like, for example, class allocation, to a sequence of some low-level operations that can be done and later actually translated to LLVM IR. We also perform then, in this phase, some method dispatches, because finally we have some additional information to this and some real memory layouts on which we can rely. Also, we can inject some handling of runtime exceptions. So, for example, all the null checks, class exceptions, etc., they are all injected in this phase of the compiler. Also, we are here performing one additional that's called elimination phase. So some files that are never used, we can easily remove them. Next, I'm just almost finishing. So new translation phase. Here we are actually translating an error to LLVM IR. So basically, we are just adding some headers needed for the compiler. So, for example, target triple, default one, or the one specified by user, so we can cross-build our application. We also provide some deconstitufying of some values, so they are defined in once and are reachable in the global state. Also, we can generate some external dependencies and translate an IR to LLVM IR itself, one by one instruction. And finally, we get some output files which can be compiled using Clang. So yeah, Clang, here we can basically compile all the sources, both the one that are coming from external dependencies, because you can store your code in resources and it will be compiled at the phase, as well as our own dependencies like garbage collector, some exceptions handling mechanisms, etc. And finally, when everything is compiled, everything is fine, we can finally link our library to either executable application or to a shared library. That's quite a new feature that is coming to come in one of the next releases. I hope so. And basically, I'm running out of time, so I would like only to give you some hints. What are we going to do with Scala Native in 2021? So basically, our main goal, basically two main goals, support for multi-threading, which it's still lacking, unfortunately. However, it's a quite difficult task to implement this, and to be sure that it's working correctly and it's simply stable enough. Also, the other part is providing a front-end for Scala 3. So basically, it's defining another compiler plugin that will be this time attached to Scala 3 that would generate for us NIR files that we can reuse in Sbt Plugin. Also, as always, we want to extend our subset of Java Center library. So, for example, with adding multi-threading, we probably add a lot of new stuff that is related to this, as well as stabilize whole Scala Native platform, as well as provide out-of-box fixes and some known performance improvements that can be still done to make everything work a bit faster. So basically, that's everything that I managed to squeeze in this really short presentation. If you have any next questions, don't hesitate. You can reach me anytime at any of the links shown on the screen.